Okay, so today I'm going to be using the guided notes you picked up at the door to complete your 8th grade review. I'm going to talk pretty fast, but feel free to pause the video and fill things in, and you can also revisit this. So let me share my screen and we will get going. Okay. All right, so as we've talked about at the very beginning of the year, and that's been an ongoing theme throughout the year, is that matter is anything that has mass and that it takes up space. And so what actually is mass? Mass is the amount of matter in an object. And we measure that in grams, and we calculate that with a triple beam balance. I know this bottom part is in red, but you do not have to copy that down. So simply that is telling us, though, that even though things can have the same volume, right, they can take the same amount of space up, they're going to have different masses. So thinking about a bowling ball and a basketball, same volume, different masses. So matter is anything that has matter and it takes up space. Matter has 3 different states, and those are solid, liquid, and gas states. So if you remember the song, oh, a solid keeps its size, not its shape. Wait, I said that wrong. Oh, a solid keeps its size and its shape, and a liquid keeps its size but not its shape. But the one that's not the same has 3 letters in its name. Oh, a gas doesn't keep its size nor its shape. That's what this is showing us. In a solid form, the particles vibrate in place, and they're most dense in a solid. In a liquid, the molecules are flowing over each other. And then in a gas, they're moving about the most. So they have the most amount of energy on a gas, the least in a solid, most dense in a solid, least dense in a gas. And then to change between the states, you either add temperature or you remove temperature. And so that's what this is talking about, is that a phase change is a change when matter changes from one state to another. And this is a physical change because it's not chemically changing its molecules. And so this occurs when energy is added, heated up, or removed down. So when we go from a solid to a liquid, we are melting. So we are adding heat because the particles are going to start moving faster. If we're going from a liquid to a solid, those particles are slowing down, and they're because the heat is being removed. Same between a liquid and a gas is evaporation. So they're moving faster, heat is being added. If it's from gas to a liquid, condensation. All right, so weight is different than mass. Mass is going to be the same no matter where you are on Earth. Weight is the amount of gravitational force on an object. So you may have seen on a recent study island, it was referring to gravity as weight. And that is because weight is the gravitational force. And we calculate gravitational force / weight in newtons. And we do that with a spring scale. So mass, same throughout the universe. Weight is going to depend on the gravitational force. So that's going to change depending on where you are in the universe. So I said at the very beginning that mass is different than, matter has mass and volume. And so volume is the amount of space an object occupies, right? So we measure that in milliliters for liquid or cubic centimeters for solid. So 1 milliliter, though, equals 1 cubic centimeter, okay? So how we calculate this, if you remember, if it is a rectangular object, we're going to use length times width times height. But if it's an irregular object, like a rock or anything that is not cubic, like a marble, you're going to do water displacement. So remember, you figure how much volume you have in a graduated cylinder, like you see at the bottom here, and then you place the object in, see how much the water rises, and then you subtract to find your volume. If you remember the video where the guy got in the bathtub, Eureka, same idea here. Okay, so this all ties into density. So then we can use the amount and volume of an object to find its density. So density is the amount of mass in a certain amount of space. So you calculate this by grams per milliliter or grams per cubic centimeter. Grams per milliliter is when you have it with a liquid. Grams per cubic centimeter is when it is a solid. And you calculate it using the formula I heart density. Remember, density equals mass divided by volume. And this is going to give you how dense objects are. Solids are your most dense because the particles are close together and vibrating. And then as we move from a liquid and then to a gas, it's going to be the least dense. Okay, so remember we did the experiment with the Diet Coke and the regular Coke, and the regular sunk while the Diet Coke floated because of the amount, the changes in density there. All right, moving on to chemical versus physical properties and changes. So a physical property is observable and it doesn't change the substance identity. A chemical property is ability for a substance to change into a new substance with different properties. And so that's important to know when we come to physical and chemical changes. So a physical change, it changes from one form to another, but the chemical identity stays the same. So for example, appearance and shape, appearance, state, or size. Like if you were to take a piece of paper and rip it up, that would be a physical change. Or melting of ice is a physical change. It is still water. The molecules are still hydrogen and oxygen in an ice form and in a water form. Then we have chemical changes. Chemical changes change into chemically different substances. So the changes are irreversible, like burning a piece of paper or rust forming on a nail. All of those are going to be chemical changes. Remember when we did the glow stick lab, increasing temperature speeds up the rate of a chemical reaction. So you're going to, if the temperature is higher, the reaction occurs faster. If the temperature is lower, it's going to occur lower. Evidences of chemical change include color change, temperature change, a production of a gas, a production of light, and taste and smell change. So both chemical and physical changes support the law of conservation of matter. So the law of conservation of matter and mass states that matter and mass cannot be destroyed or created, but it can simply change forms. So think about when we did the lab with the Alka-Seltzer in the bag and how we measured before and after the reaction and it had the same amount. Or this is a good image up here. You have parts of a plane, you put the parts of the plane in together to make the plane. That's the same amount that was there before is the same amount after. Remember, we also talked about this with the carbon cycle and photosynthesis and cellular respiration. Those all support the idea that when we are, what we have at the beginning in a closed system is what we have at the end. Okay, into atoms. So atoms are the smallest part of an element and it has all the chemical properties of it. So we said it is the smallest part of matter. So all matter has atoms, and atoms combine in various different ways to make molecules or compounds. So each atom is made up of 3 subatomic particles. It's made up of protons, neutrons, and electrons. Protons are positive. They have a positive charge. Neutrons, no charge, neutral. And electrons are a negative charge. So protons or neutrons are going to be found in the nucleus, and the electrons float around in the electron cloud. The differences in the amount of protons, neutrons, and electrons that we have gives us the different amount of different types of elements. So that's what relates to what we're talking about next, which is your atomic number and your atomic mass. Remember that most of the mass of an atom is found in the nucleus because that's where the protons and neutrons are, and the electrons are the smallest of the subparticles and are the subatomic particles, and those are found again just in the outside cloud. So the number of protons in the nucleus of an atom is the atomic number. So each element has its own unique. So that's what I was just saying. The total number of protons and neutrons in the atom is the atom's atomic mass. So if you look here, the very top, if you look at the periodic table or you look at the elements listed, you see that the very top is going to be the element name. And then the next is the atomic number. So this is the number of protons, and it's actually also the number of electrons, because remember, protons is positive, electrons is negative. In a stable atom, those two are equal so that there's not a change in charge. So the atomic number is also equal to the number of protons and the electrons. The letter in the middle is the element symbol, and the number at the bottom is the atomic mass. And since I just said that most of the atomic mass is found in the nucleus, the atomic mass is also the number of protons and the number of neutrons. So we can use that information to find out how many protons, neutrons, and electrons an atom has. And we can do that using this saying, and we talked about it, but I think a lot of us forgot what ape man means. So if we can remember, ape is the atomic number, so the number at the top equals the number of protons and equals the number of electrons. So if we look back here, 9, that means that we have 9 protons and 9 electrons. Now the atomic mass minus the atomic number gives us the number of electrons, because the mass, atomic mass, is the number of protons and the number of neutrons. And so since we know that the atomic number is the number of protons, we can subtract that number from the mass and get the number of neutrons. So if we can remember, if we need to find neutrons, do man. If we need to find protons or electrons, use the ape. So if we go back and look at fluorine, we would subtract the atomic mass from the atomic number to get the number of neutrons. So we would round this up, it'd be 19 minus 9, so there would be 10 electrons. 10 neutrons. So there's 9 protons, 9 electrons, and 10 neutrons in fluorine. All right, so all this came about due to the atomic theory model, and the atomic theory model is going to tell us how an atom looks and behaves. And one reason, and I think the main reason they would test you on this, is that as new evidence is gathered, it's going to change the model. So remember, theories can change as new evidence is gathered. So this shows you the history of that information. So you have a solid sphere, the plum pudding model, the nuclear model, the planetary, and what we have now. You don't have to remember each of these, but you do need to remember that the model tells us how atoms are arranged and what they look like. And then they have changed over time as new evidence was gathered due to technology. So elements are arranged by atomic number and are grouped by their physical and chemical similarities on the periodic table. So there's about 90 to 98 of the 118 elements are found naturally. So we're going to spend a little time. I'm going to go over the periodic table because we went through this very quickly because it was right before Christmas and you probably don't remember most of it, okay? So this is the periodic table, and elements that have similar chemical and physical properties are arranged in groups. So these groups are horizontal. So if you look at the periodic table and you see horizontal, these, like if we're looking here, the purple ones all would have a similar chemical and physical properties. Same in the blue, same in the orange, same in the red. So the groups which are horizontal, vertical, oh my goodness, I've been saying horizontal, vertical, so these vertical columns are called groups. So if you look here, alkali metals, alkali earth metals, the transition metals, then we have halogens and noble gases. These are groups of vertical columns, groups or families, and then they have similar properties. Group 18, which is the last one, is noble gases because they are very non-reactive. So that means all of the ones here are not, they have similar properties. Now, the horizontal ones are what we call periods. And in these horizontal rows, they have chemical properties that tend to change the same way that belong. So from left to right, the atomic mass and number increases. So as you go across, atomic number increases. These are periods. Now, most materials or elements in the periodic table are metals. So you will see this little like zigzag line down the side of a periodic table. And down that side to the left of that is metals, and there's 91 metals. To the right of that, you have metalloids and non-metals. Metalloids are what you can think of as a transition between the two, and then non-metals are going to be your gases. So if you're asked what is majority of elements in the periodic table, metals. And that transition line is going to show you metalloids and non-metals. So it shows you the changes in them. So atoms, like I said, are the basic units of matter, and they can join together to form the following. They can form elements, which is a single type of atom. They can form molecules, which is when two or more atoms are bonded together of the same type, the same element. A compound is when two or more different elements are bonded together chemically, like water. Hydrogen and oxygen is a compound. And then we have mixtures, and mixtures are different compounds and elements mixed together physically. So looking at that picture down there, you see that atoms are of a single type of atom. So fluorine that we were talking about, it would just be a single type of atom. Now, molecules of an element can come together, and we have a lot of elements that only exist in our atmosphere as molecules. A good one is oxygen. You often see it as O2. That means two oxygen atoms are together. These are molecules because they are of the same element. A compound is when two or more different elements are chemically bonded. So for example, water, two hydrogen, one oxygen. They're chemically bound together and we get water. And then finally, a mixture. This is when we have different compounds, elements all mixed together. And we have different types of mixtures. We have heterogeneous and homogeneous mixtures. So heterogeneous, they are not evenly mixed. So remember we did the lab with the Chex Mix. We did it with the Chex Mix, and that Chex Mix had pretzels, and it had corn Chex, and it had wheat Chex, and it had the wheat bites, and it had all these different things. They were not evenly mixed. So we pulled some out. We maybe had 3 Chex Mix and 2 pretzels. That would be a heterogeneous mixture. A homogeneous mixture are evenly mixed together. So like the Gatorade that we had, we couldn't separate the Gatorade and the water and the sugar. They were all mixed together. Or salt water in the ocean, they're evenly distributed. So if the elements and the compounds are evenly distributed, this is a homogeneous mixture. And because they're homogeneous, we call that, they have what we call a solute, solvent, and it gives us a solution. So a solution is a solute that is evenly dissolved into a solvent. So a solute is what's being dissolved, the solvent is what's dissolving, and together they get the solution. So elements, compounds, and mixtures can also be measured using a pH scale. And the pH scale is going to tell us how acidic, basic, or neutral something is. So the pH scale measures how acidic or something basic it is. So the lower the number, the more acidic, the higher the number, more basic. So 7 is what we consider neutral. So from 1 to 6, acidic. From 8 to 14, alkaline or basic. And this is just saying like how the hydrogen molecules are reacting, but know that what you have to know is related to the pH scale, the lower number, acidic, the higher, basic, 7 is neutral. All right, so talking into waves. So remember, waves transfer energy. So we're moving now into physics. Everything before now was chemistry, now we're into physics. So a wave is energy, and it's a traveling disturbance that moves energy from one place to another. And mechanical waves need matter to move through, and you can have longitudinal or transverse waves. So like sound waves that you see going on below are going to be transverse waves. Longitudinal waves are going to be, wait, I think I got that right. Let me double check. I think I got that one backwards. Oh yeah, oh no, I did. So longitudinal waves are like sound waves that bounce back and forth. Transverse waves have the up and down. Okay, so waves have measurable properties, and one of those measurable properties is frequency. And this is the more waves that pass through a certain point in a certain time have a higher frequency. Remember, this is an inverse relationship to wavelength. So the higher the wavelength, the least frequency, the shorter the wavelength, the higher frequency. So if you look at this very first wave here, you see at the top, there's long wavelengths between the crest and crest or troph to troph. But that means the frequency, the amount of waves that pass a specific point, is low. But if I look at towards the other side, the frequency is very high because there's a very short wavelength. You can also see it at the bottom. The red wave has a long wavelength, short frequency, because not that many waves are passing this specific point. Quite opposite here to the blue waves. They have a high frequency, shorter wavelength. So again, waves have different parts. We have the top, which is the crest. The bottom is the troph. The distance from resting to the top of the crest or from the rest position to the troph is what we call the amplitude. And then wavelength is the distance from crest to crest or troph to troph. So another type of wave that we studied was the electromagnetic wave. And electromagnetic waves are made of vibrating electrical and magnetic fields. And these do not need matter to travel through. So mechanical waves need matter to transfer through. Electromagnetic waves do not. So they can travel through the speed of light through a vacuum. And each part of the electromagnetic wave has a different function. So you see we have radio waves. These have the least amount of lowest frequency, longest, low frequency, high wavelength. So long wavelength, low frequency, then microwave, then infrared. Right here, kind of in the middle is visible light. That is the only part of the electromagnetic spectrum that our eyes are able to see. And then remember, if we see green, like a leaf is green, it's because that plant is absorbing all the wavelengths except green and reflecting that green. Then as we move down the electromagnetic spectrum, we have ultraviolet, and we're getting shorter wavelengths. So that means a higher frequency. So the highest frequency is going to be gamma rays. So light has the ability to pass through objects, and as it passes through objects, it can interact with that object differently. Remember, we all have behaviors that are different in the classroom or different with our friends. Light also has interactions and behavior. It's different with, with the objects it's interacting with. So items can be transparent, which means it allows all light to come through. It could be translucent, letting some light pass through it, or it can be opaque, letting no light pass through it. And then also those objects can cause light to change directions or interact with it differently. So we can have absorption. It's exactly what it sounds like. That object is going to absorb all the light. It can have reflection, a bouncing off of the light. It can have a refraction where it's bending, a diffraction where it's moving about, or scattering where it's being pushed apart. Think about those labs we do. A mirror is going to cause a reflection. Water causes refraction. Black objects that are opaque often are absorption. If you shine a light through a hole, it's going to diffract, it's going to go through and go out. All right, moving into energy. So one type of energy that we studied was thermal energy. And thermal energy is the total energy within an object's moving particles. And we measure this in temperature. So temperature is the measurement of the average kinetic energy of the particles. And it's measured in Fahrenheit, Celsius, and Kelvin. So we mainly like to measure it in Celsius and then sometimes in Kelvin. All right, heat. Heat is transferred of energy from an object of higher temperature to an object of lower temperature. So heat is going to continue to flow until the temperatures are equaled out. So you see the heat is transferred from the object with higher to the object that is lower until that is equal. Once that is equal, then the heat transfer stops because the particles are now moving the same. Okay, so remember, watch the video that there's no such thing as cold because objects are literally just pulling heat. So if we go outside and the particles are moving slower, you are going to give some of your particles to the atmosphere, causing us to become colder because our particles are moving slower because we've given some of our heat away. Remember, girl, your particles must be moving fast today, means that they are warmer, they are hotter. All right, so heat can be transferred in a few different ways. It can be transferred through conduction, convection, and radiation. Conduction is when heat transfers by touching. Convection is transferred through water or air by the circulation. So this causes heat to rise and cold to sink. And it does that because of changes in density. The changes in density cause the warm is more dense than cold. Warm is less dense, cold is more dense, so it pushes down. And that circulation causes heat transfer to occur. It continues until it equals. Remember, that's part of how the sun works. It's why it's warmer upstairs. It's also how water is boiled. And then radiation is that heat transfers through electromagnetic radiation. So like the sun energy is considered radiation. So energy exists in different forms. Energy is the ability to cause change. So energy is moving energy that depends on mass, or kinetic energy is moving energy, and potential energy is stored energy. Both kinetic and potential equal mechanical energy. So mechanical energy is the energy in motion, stored energy is potential, kinetic is moving. Both of those together is mechanical. And that's what it says here, the energy that moves objects. It could be kinetic, potential, or both. Sound energy is energy associated with the transfer of vibrations. Chemical energy is going to be energy stored in chemical compositions like food or glucose. Remember, it is used, chemical energy is made during photosynthesis. It converts light energy from the sun into chemical energy in the form of glucose. Then we have nuclear energy. Thermal energy is the amount of heat. Electromagnetic is going to be energy transferred through electromagnetic waves, and light energy transferred through the sun. All this supports the law of conservation of energy, that energy is never created nor destroyed, but it can change forms. Most of the time, heat or sound energy is a byproduct of heat transfers. Remember, any of these energies can be transferred back and forth to each other, supporting the law of conservation of energy. Because as it transfers, that energy is not lost, but it's changing forms. So motion of an object can be described and predicted. So motion is a change in position, speed, or in position. Speed measures how fast that position changes. And when it's done, it's speed over time. So it's a relationship between the distance traveled in a specific amount of time. And then velocity is a speed with direction. Remember, like a tornado is heading 20 miles an hour northwest. And then acceleration is a change in velocity. It can be either the speed or direction, because simply acceleration is a change in velocity. So you see here on the left, this is a speed chart. You see distance over time. A is traveling quicker than B. A also travels at a constant speed because you see that it's a straight line. And then B had a constant speed, and then as it curved, it was speeding up. And then we've used this image to the right that if it's speeding up, slowing down, or changing directions, it is all acceleration because there's a change in velocity. Now, velocity is its speed and a direction. So remember, a force is a push or pull. It is measured in newtons. And a force is a vector, meaning it has two properties. It has both direction and magnitude. So when forces act on each other and they're equal, it is considered balanced. If one has more force than the other, it is unbalanced. So you can have contact or non-contact force. Contact force is literally touching of objects that cause a push or pull to occur. This would be pressure, friction, causes that not to occur anymore, and air resistance as well. Then we have non-contact. So this is force that is happening at a distance. We have gravity, magnetism, and electrical force. Gravity is going to have a greater mass equals stronger gravity, greater distance, weaker gravity. And then net force. Remember, if they're working together and it equals 0, balanced. If one is more than the other, net force is going to, if it's more than 0, it is unbalanced. And then these are the 3 laws. And that is it. If you finish early, please go back and work on your study guide or any study islands. You owe me. And I will see you tomorrow.